So this is the video needed. This is the video needed regarding the semester project. So we were building a fire alarm. So this is the presentation that we showed Ma'am Aruj. A quick overview of this presentation is that a very high number of people die in fires every year, and these numbers are usually already set, and they already have a range, and these ranges are from 100,000 to 120,000 to nearly 200,000, and 50% of these lives are saved by fire alarms, meaning that if fire alarms didn't exist, these numbers would have been doubled. So that's approximately 400,000 to 250,000 people that would die. So this is why fire alarms are very important. It's an early detection of fire hazards, saves lives, reduces damages, ensures complies with safety standards. I mean, the important part is that you can keep yourself safe, your family safe, your materials safe, your house safe. I mean, if s- smoke is coming from some specific segment of the house, you can close it down so the damage can only be preserved in that one area. So this is why fire alarms are extremely important, and we will move on. This was one of our inspirations regarding the fire alarm, something we saw in the start. So we had an idea that this is something that could be started. So the components we used were a 10K thermistor, LM358N op amp, a resistor, a 10K potentiometer, a 5 volts buzzer, and a 9 volt power supply. So we will continue to the block diagram. Block diagrams are very simple. The input would be a thermistor. So whenever a thermistor gets heated up, the working of a thermistor is as the temperature increases, its resistance decreases. So whenever a thermistor will get heated up, current will pass through it, more current will pass through it, and then in the middle we will have the LM358N and a potentiometer, and the output will be the buzzer. So once the thermistor gets heated up and the resistance decreases, the buzzer starts buzzing. So this is that. A quick diagram of the LM358N would be this. So the LM358N is more of a comparator, which compares the values of the both inputs. If this would likely open, so it's a comparator which compares both the values. And yes, and in our project we only used 1, 2, 3, 4, and 8, not 5, 6, 7, because we only needed to use one comparator, not both. So we had only these. We only used one side of the comparator, and this is the op amp that we used. Next I can show you the theoretical work. These are the theoretical work values. Yes, so the theoretical work was done by Mohib, and basically he did this. He used mesh analysis for the most part. What he did not do is he did not go above the op amp to find out the current going into the buzzer, because he did not understand how to successfully work across the op amp. So these are the values. This is all the working, and these are the final values regarding I1, I2, and other values. So these are the total 9 volts that go into the output. So we even tested these values, and when testing them via DMM, we found out that they were very similar. Of course, not all the values weren't gonna be 100% same, but they were very closely similar. Next, we can move on to the simulation. This was our PCB. It's a very simple PCB. This is the thermistor. This is the resistor. This is the potentiometer and the DMM. over here we have put a buzzer, but in this case of the simulation, to show that the simulation works, I have put a LED. So when the temperature of this will increase, the voltage of this will decrease, the resistance of this will decrease, and the current will direct travel through this. This is the simulation is running, and you can see that the simulation is running. The installation of the button is a bit ambiguous because it doesn't really fully work. But if we had inputted it in the PCB, it would have worked. We even made specific holes for it. So we can continue. The PCB, we were not so complex. We were not so understanding of the PCB. So the few issues we were facing regarding the PCB was that the sizes, like the size of the potentiometer and the size of the resistor, were very different in reality in on the PCB. One was extremely large and one was extremely small, and these various in sizes were taking place a lot. So we replaced them with capacitors and the T block. The T blocks were for this T block was the button. This T block was the input which we used, and this T block was for the output. These two capacitors were one. This was the potentiometer. Sorry, this was the thermistor, and this was the potentiometer. We had a 3-pin. Sorry, this was the thermistor, and so this was the resistor. We had a 3-pin potentiometer, which we were using. So the one we were using in here, its size was extremely large. Hence, we actually changed it out for this. I have forgotten what this was, but we changed it out. This wiring was a bit hard to do because of how much it overlaps. So we had one singular potentiometer wire which went between the two ports, and this was a bit hard to make on the PCB sheet, because when imprinting, if these connected, it would have caused us large trouble, and it's hard to cut. So next we can move on to the, I apologize sir, working and testing. So the working can be done simply. uh, so this was the first breadboard made. This was the first breadboard made, and it was working. This was a working breadboard. Sorry, this was not a working breadboard. This was the first test of the breadboard, and whose troubleshooting was needed to be done. And this button was troubleshot a lot. And then this was our first working breadboard, which was fully working. And this is the buzzer that started buzzing after you have increased the temperature. So this was a fully working breadboard with a working buzzer. Next we can move on to the rest of the working. We can show you that this was our PCBs. This was after importing. We had a very small layout. This part of the layout, if I can just tell you the issues, this part of the layout was a bit hard to do because these wires are very close, and even you can see in this that the person who has imprinted this, I mean the printer at the shop, even when he's done it on the paper, these wires are connecting, and even these wires are connecting. These holes are connecting. So these were small parts that we really needed to look out for and change. And even when you imprinted this on, we can clearly see that barely this is actually probably connecting, and even these are connecting. So we really had to make them cut. Really had to cut them again and again. The issue that I had mentioned before was this. This is the big potentiometer, and this is the PCB. And we were facing issues like this in the start, that the size difference is a lot, and more so that we cannot extend the legs of the potentiometer so much. So we were facing issues like these, which we solved. It's just random wiring. uh, then we can continue with this. this was this is not our PCB. This was our PCB. There's a video of us in the room while we are this is the video of us in the room while we are doing the FECL, while we're using the FECL for to have the layout ready to print it on the copper. For some people it happened very quickly, for some people it took lots of time. These pictures, we actually originally we used this for the potentiometer, but later we came back, and then when people were actually having a discussion with the seniors, we showed him this, and also happened that he made us change it into the other smaller one, which actually came out to become bad for us, because this still had distance. The legs were of the potentiometer were very much fixed, and this would have actually worked perfectly, but he made them very close, which actually caused us great trouble. So we realized that not always seeking help from a senior is not beneficiary for us. We can continue this wiring. This is just bad wiring that we were facing. So after all of that, this was the face of our circuit. It's very basic circuit. This is the T block. We were unable to find a good switch, so we had to replace the switch with a short circuit right here, as you can see. This is the input for the battery. This is our resistors. This is a 10k resistor. This is our potentiometer, which was a bit hard. This is our IC, and this is the buzzers. It's a very small circuit with basic components. This was soldering done. There's a few problems in this soldering, which I can elaborate. So we had to short this out, and then we had to cut the copper in the potentiometer, because of the problem I had showed you earlier, that all of these were actually touching, so they were all shorting each other. So we had to cut those, and because of that, we accidentally cut here, so we had to put lots of solder here so that it could short itself, so that the parts can reduce. We also had to short circuit from this output of the potentiometer into this IC, because this wire, this line that I mentioned before was a trouble for us. It connected to both of these terminals, so it was shorting, so we could not actually figure out a way to correctly cut it. So what we did instead is we cut one line here, so that the current does not travel through these, and we cut sides of this so that it does not travel to each other, the ports, and we directly just shorted it to the port. So we can continue. G I apologize for the trouble, sir. So if I can just zoom out. Ready, sir. I apologize. So as I was saying, so this was a problem we were facing, that this line started connecting to both of this 4 and 3, and hence we had to cut both sides